hi everyone, I'm Christian. Today we're going to talk about Driver, which is an agentic virtual machine in Rust. First of all, as I said, I'm Christian. I'm the founder of Creators, and a startup in an applied research in autonomous systems startup. And as part of this research, we came to Driver, which, as I said, is a virtual machine. First of all, we are going to talk about what is a Turing machine to understand the foundations of what is an actual computer, and then try to build on top of that. So basically, a Turing machine is a mathematical model of what is an actual computer. It has a wired behavior machine, a tape, and a head. Basically, the head reads the data that is on the tape, and the wired behavior machine is a wired behavior machine, as it says on the text. So basically, you could have here a machine that makes an addition of two numbers, and you have the numbers encoded on the tape itself. You could have here a multiplication machine or any other kind of machine. As part of this concept, Turing said that with that you could build a universal Turing machine, which is basically a machine that, reading from the tape a machine definition itself, it could imitate another machine. And on your wired behavior machine, you could have an interpreter, which, reading the tape, knows what it has to imitate, and then with the data can build that behavior. So we will have, first of all, the definition of the machine, and then we will have, for example, in this case, an instruction, which will be 13, and 13 in this case, let's say it's something like print. You could read 13, print the hello on a printer, for example, and then pass to the next instruction, which will be 58 in this case. Let's see how we can build a Turing machine, a very basic Turing machine in Rust. And then on top of that, we will go to Driver. So this is a very basic Rust project. It's been, so why? Perfect. So here we have only a main RS with these lines of code. We have basically the tape, which is a vector of bytes, the head, and our state. Basically, we print the current state of the tape, and then we have the wired behavior part, which is basically all the stuff that I just mentioned about the behavior of the machine. Here we have the current symbol. Symbols are calls to these values that are inside the tape, which means each part of the tape is a symbol, and we can work on those symbols. So here we match the current symbol. If we have a 0, we invert the value to 1. If we have a 1, we invert the value of the current tape to 0. If we don't know which symbol are we looking to, we only halt the machine, which is stopping the machine. So after this, if the head plus 1 is bigger than the tape itself, means that our program is running out of the bounds of the tape, so it's finishing the execution. So we halt here, and otherwise we increment by 1 to go to the next instruction. After this, we can print the tape itself. So if we take a look to this part, we are only making a machine that inverts values of the tape itself. If we execute this, let me clear this. Here we have the tape start, which is 10110, and then we have inverted the whole tape. So this is a Turing machine in Rust, a very basic Turing machine, but we can see all the parts that we just mentioned here on a very basic stuff. Let's now take a look of the Driver project itself, which is a virtual machine which is a Rust workspace with 4 members: core, bytecode, compiler, and CLI. Today we will focus only on core, which is the virtual machine itself. It's all the Turing stuff. So let's start with core. Core basically has a librs file, which has a new public method, which defines a new virtual machine. It's a constructor for a virtual machine. And given a bytecode, which is the same concept of a tape, but basically instead of being a tape of symbols, is a vector of bytes, but it's the same concept. So we build a new virtual machine with this. But what is an actual virtual machine, or what it looks like? So it's this struct. Basically, it has an operand stack, which we will explain later. It has a call stack, memory, bytecode, program counter, and handlers. This bytecode, as I just mentioned, is the tape, and this program counter is basically the head, where it points the current tape. And the call stack is all the call stack that everybody here knows, that we have a call stack with different calls and the scope of the current call. So with this struct, what we can make, because right now we can initialize a new struct with a VM, with all this stuff, but what we can make? So we can run the machine itself. So basically here on the run method, first we made the prelude thing, which is on the virtual machine's wording, basically loading all the stuff that you think that it will be loaded when you run a machine. Basically, things like printing values, things like all the built-in methods and all the stuff. And then we run the bytecode itself of the machine, which is running the tape or running the program. Run bytecode method is this one. It's a little more complex of what we just have seen here, but it's the same concept. We have a while with a match. Here we have our while with our own match. But since this is async Rust, which everybody here knows that async Rust is great, it has this kind of signatures with the box future and then pinning the future itself to have it available. So here we have our current head, which is the program counter, and here we have the bytecode, which is the tape, and we try to not be out of the bounds of the tape itself. And here we make the match, which is this match, to know on which instruction are we right now. So in this case, we first of all take the current symbol or the current byte, and we pass to an opcode. Basically, an opcode is the name of an instruction or of the symbol, but on the, again, virtual machine's wording, let's say. It's an operation code. So in driver, we have 24 opcodes from load const, which is the more basic one, because you want to load some stuff on the memory, let's say. But basically, we have load const, load bar, store bar, and jump, for example, function declaration, and all this stuff. Let's take a look to load const, which is the very basic one. And basically, load const is defined as 0x01, which is a byte with 1. And it loads a constant value onto the stack. This stack, we will explain later how this stack works, but basically it's a stack of the operands stack that we just mentioned on the VM part. We have on the tape itself, or on the bytecode, we have the load const instruction. Then we have the data type that we want to load. If we want to load an i32, for example, or if we want to load a string, it will be different this type. And then we have all the data that will parse based on this type. So if we take a look to the actual code that is built to load a variable to the const, we have, first of all, we increment the program counter. Right now we are not on the instruction itself, we are on the data type. So we increment by 1, we're on the data type, and then based on the data type, we get how many bytes will fill that data type. For example, if we have i8, you will be on 1 byte, which will mean one length only of data, because it only fills 1 byte. So based on this, you get a data type, you get the value bytes itself, and then you pass this 2 bytes to data to given a data type and some bytes, it gives you the actual value that you want to store, and then you push to the stack. When we say you push to the stack, we mean that, for example, given this code, let a equals 1 plus 2, you will have, for example, this is assembled bytecode, which is the tape but with some meaning. You will have something like load const of data type 1, which will be an i32, and 2 of these, which will be 1 and 2, and you will have here 1 and 2. And you are loading both variables to the stack, which is this operand stack, which will look like 1 and 2, and then the addition opcode will add the 2 values that you have on the stack. If we take a look of what is an actual value, because here we say that, okay, you here gets the actual value of the bytes, which value is this? For example, if I have an i32, it's not the same that if I have a string. How can I handle this on the stack itself? So we have an enum that builds together both the data types. First of all, we have the raw values, which are primitives, are passed by copy, and then we have the handles, which are basically the shadow refs, are passed by shadow refs, and are the objects. And then, for example, to take a look to the raw values, we have an i32, i64, and booleans, floats, etc. Let's take a look then to an actual execution of this program, for example, to this kind of programs. We have a compiler, as I said, which is the compiler for a programming language called Ego. Basically, we compile the program to the actual bytecode of driver, and then we can execute the driver that way. So if we go to the code again, let's take a look to the first example, which is a main.ego with only 4 print statements. So if we run this, with driver run 1, it will print the values, which makes total sense. But let's take a look of what is actually happening here. If we take a look to the execution with the -d flag, you can debug all the execution. First of all, we have all the Elixir tokens. It basically, we pass this file to have some tokens for them to build a tree. And then from this tree, we basically build the actual bytecode. This bytecode looks like what we just have seen on this slide. Basically, we have our load const of our println instruction and our load const of the actual value. And then we call the println function itself. So this way, we start building all the pieces that we want to build to make some kind of execution. If we take a look, for example, to where this loop, we can create a variable called count, and then we can start iterating until it has 10 iterations. So we increment the value by 1 to go step by step. But basically, if we run 1.1, we'll have from 1 to 10 based on, basically on this code, basically prints the count. And we can also, again, see the debugging. If we can take a look here on the runtime section, which is the actual execution at runtime, we have too many more stuff because since it's a loop, it will go every time over that part, which makes sense. And we have also all the Elixir stuff, but the disassembled again bytecode, which all the .const, store bar, and all the stuff. Here we have jump if false, which works for going back again to the loop if something isn't on the right path. So you can move the tape to another path and go again to that execution. And then also, we can import native modules. So these native modules, for example, would work like 1.2. And we given the fs native module and read file method, we can read the given file. In this case, we are reading the first example file, and we're printing out to the standard output. So we can also, for sure, we can also read some absolute paths, which I just leak my bank account secret. But basically, we can read the stuff from an absolute path. And as we have seen, we can use import to import other native modules, but also other Ego modules, which are basically the compiled bytecode. So we have FS, we have IO, HTTP, net, and more stuff. But there is one module which changes everything on the driver virtual machine itself, which is the AI module. Basically, the AI module has different members, has different types, but basically what it makes is that it turns LLMs, that everyone is talking about right now about LLMs, it took LLMs and it converts LLMs outputs into execution. It has different methods, run agent, add action, add context, and different types, but the more important method will be run agent. Basically, run agent has the ability, we will dive into the run agent stuff right now, but basically it has the ability to execute things of the standard library itself by an autonomous execution. So the run agent method, basically given a task input as an argument, it generates a plan with different steps, then it iterates over each plan step in an outer loop, and then inside each step it will again iterate to try different actions that completes this step. That way we can, after making all the back and forth of the both loops, we can generate a result making each step successfully completed. And we will have a plan result. If we take a look to how it's actually built run agent, this is the actual run agent code, but it's a simplified version to not make all the details. So basically we have the run agent, we receive the machine, we receive a prompt, an end condition, and first of all we generate a plan, then we send an event with the plan. This event system, then we will see for what it works, but basically we report every time is something happening inside the run agent stuff to have observability outside this function. So we generate a plan, Then we generate a context, an error counter, a steps counter, and we start iterating over the steps itself. We send an event every time we start a new step, and we have a counter also for inner iterations and to check if the step is done or not. When we are on the inner loop, we basically check if we just like end our max inner iterations, which is defined here on top, which are 8. And after this, we basically generate an action for that step. An action, as I said, will mean that you generate an execution of the standard library itself. For example, the fs write file action will be called from here too. We will dive into that right now. So then after this, you emit an event every time you generate an action. You here execute the action itself. Given an action, you execute that action, and you have a result. If that result you push the result to the context based on the action that you have executed and the result, and the LLMs tells you if the step is done or not, basically here on the step done field. Once it's finished, you break the inner and you go again to the outer to start with a new step, building this way all the back and forth that I just mentioned. And once everything is done, you say that the step is done. And once all the outer loop is done, which means the plan itself is done, you generate a synthesis based on the whole prompt, the plan itself, all the context, and the return as a result with all the stuff. And we then return an agent summary. Let's take a look of how this looks in reality, how this driver machine can execute autonomously the standard library. So if we go to the AI lib, we will collapse for the moment this agent control thing, and we can import AI, FS, the M for reading the environment variables to call an LLM provider. We will not see this M right now. And here we can make what I just mentioned about the run agent method. We call AI.runAgent method, and we give a task and an end condition. The end condition is basically a way of telling the LLM that I want the execution to end if the file is getted or you cannot get the file itself. So in this case, the task is give me the content of the .secret file, which can be performed by reading a file, basically. And we pass here an agent control. The agent control basically receives every event that we just mentioned here on the run agent, and you can decide if you want to continue or not. In this case, this agent control is basically an always on. It always lets you pass all the stuff, and it will execute everything that the LLM provides. So then we output the result and the output data. If we run this, it executes the file system itself. How can I make the LLM not be outside of the bounds that I want to? So well, right now, let's take a look. Users, for example, users, no reply there, .secret. This file actually exists. In fact, let's check it here. Basically, this is an fs with file of the current file that I just mentioned. And if we execute this file, it tells you the content itself. But if we try to read this file from the agent itself, which is, again, the same path,
the file user's no-reply secret does not exist, so its content cannot be retrieved.
So in this case, the LLM just decided to use the native module of the speaker to tell me what is happening. I didn't expect this because on the demo it wasn't happening this, but LLMs, I guess. As we can see here, it does not find the file itself. It doesn't know where is the file, because the standard library is built in a way that it behaves differently when it's being executed by an LLM, and it behaves differently when it's being executed by a deterministic flow that I just programmed here on Ego. So if we, for example, that's all. If we, for example, try to escape the sandbox, which right now is a current working directory, to try to make the LLM say, hey, just make all this, normalize this, and then go and escape the sandbox, we could try again to run it. and it says that it doesn't exist or cannot be retrieved the data. But if we take the same path and we execute it, deterministically with the fs_rat file method, it tells you the content. So the virtual machine is built with some guardrails on the standard library itself. Basically, as I said, the run agent can see all the native modules, or at least all the exposed native modules, to decide which actions wants to perform based on the task itself and the whole loop that I just mentioned. We have, for example, the file system that we just have seen. We have the web, we have the HTTP, we have also the speaker that it's hallucinates right now. And these modules implement a guardrail systems to avoid the LLM to make its own stuff. For example, on the path example that I just mentioned, that we just have played with on the file system, it has this method which is resolve path with context, which basically, first of all, generates a route, then always prefix your path with this route. If you try to escape, it canonicalizes lexible the path itself to avoid, for example, symlinks going back to the actual path, but the LLM doesn't know that there is a symlink and all this stuff. But basically, it ensures that you never escapes the current path that is sandbox, which is the virtual machine defined context that you can actually say which context do you want to have or which sandbox path do you want to have, or it's the current working directory automatically. And yeah, it builds everything. So after all of this, someone could think, so why Rust? I think that we have two main things to build this in Rust. First of all, it runs everywhere. Like we compile this virtual machine for microcontrollers, for a started library that loads into Node.js, that loads into Python, and also for loading to desktop applications, and also the compiler. Right now, we have a project with plenty of lines, and we have multiple enums everywhere, and the compiler knows and tells us when we are not making correct match of all the use cases that could happen. A part of this, we are building, as I said, driver, and we have a closed beta too, as like profile, and you could access this data in the driver.creators.industries website if you want to join the whitelist and see all the stuff that we are working on. So this will be everything. Thank you so much for your time, and any question that you could have is the perfect moment right now. Thank you so much. And this is a query for the closed beta, if you want to check it.
So the LLVM just outputs the bytecode or outputs the language?
Outputs a module. Yeah, so that's a very good question. And here we have a module that I didn't mention, which is basically the output. The LLM sees this. If we run driver run, sees this. Basically, we have a parser of each native module that turns the native module into text in a way that LLMs can know, for example, that I want to use the file system search file method, which recursively lists files under a directory, and it gives the parameters that it has available, the function itself. So it generates this fs.self file.
So then self-compiles
Yeah, that's right.
Yeah, because there are some people saying that no, you don't need languages now because long enough to output like the bytecode.
Yeah. I don't know, because I don't know if the LLMs, when they are trained, they can see too much bytecode, you know? So, anything, well, it's well answered? Like, okay.
Yeah, thanks.
Any other question? Or we are done?
You consider languages like Starlark, it's deterministic Python extensible, so it may be easier to use than your custom language?
Well, that's a very good question, but when I decided to use a custom language instead of, if I understand well your question, which is why not to use another language and why build my own language? I think that it's a very good question, and I think it's because right now, all the languages that we have built till the moment, we're thinking about that they need to be understood by a human and deterministic by default. I think that there are other abstractions that maybe not right now, but maybe in 5 years, we will have on languages that works differently. Probably, I don't know, maybe they have a description on top of the file and this description is parsed by the LLM, I don't know. But I think that they will appear another kind of languages taking advantage of an actual LLM in internals, let's say. And I think that having right now this discussion puts us in a very good position for, in 5 years, having a language that works that way. It's a good, okay, perfect. Any other question? Oh.
Can you compare this with, for example, giving an agent a CLI? So you give the list of these commands, and you cannot do more specifically from those. So what would be the comparison? Because, for example, you don't need to learn an agent bash. Or interpreting some of these commands that from text, agent can interpret differently. So
that's
numbers. So that's one.
Yeah, that's a very good question too. The thing is that right now, when, for example, when we use cloud or when we use, I don't know, codecs, these machines all the time are asking us, do you allow me to make this? I already know that I don't want you to, I don't know, remove my stuff. So I don't need to tell you that I don't want to remove because I already knew. You should know too. So I think that the trick is to build systems that doesn't need to be by default not intelligent, or at least that cannot be run autonomously. I think that we need to run autonomous systems that can perform an intelligent behavior. And this driver is going towards that. So you can program something that can act independently and intelligently without you looking at every step that it takes, if that makes sense. And also, we have very cool abstractions. For example, if we run driver and we make open the ycombinator.com website, I don't know, and go to the first post. First, let's move to the beta, and right now, yes, open the news.ycombinator.com website and go to the first post and generate a summary and send me the summary result, for example, to social@creators.industries. I don't know what it will execute right now, but it will open my browser, it will start searching, and you can extend these modules as far as you want. For example, you could take, well, here is making all the stuff. You could, for example, take a picture. You could, for example, use a speaker itself. You can write the modules itself. And if we take a look here on the beta, we can define our own tools. So you could have here an email tool. And it's the same as the native modules parsing that we just have seen here on the standard library.ego file. If we take a look here, just open the link itself. It generates the whole summary and it sends me, well, right now it's bad process because I think that resend just blocked me because I made too much tests. But basically it sends the email with the custom defined module, which is this one. So that's why I think that Bash is not a very good solution, because Bash assumes that you are intelligent enough to not remove recursively your own root. But I think that LLM, right now, the state of the art of the LLMs is not there yet, probably. if that makes you. What?
Other question. I guess you're kind of guardrailing a lot to make it safer, right?
Can you make it more louder, please?
I guess you're guardrailing a bit to make the whole story a bit safer compared to just using Python to another one. Are you still afraid of prompt injection in a way that you could escape and suddenly you go to the browser and download Python to run a script?
That's a very good question, and I don't have an answer yet. I mean, I have an answer, but it includes running your own models on your own infrastructure. Probably, I made text with our own models running inside of this machine, and driver itself having the control of the context window, which are system prompts and which are not. But the state of the art of open models and our own hardware is not there yet. So that's the main problem, probably. Because if you want to run, for example, I say an 8 billion can perform this kind of operations. It can make it, but it's not working well. So if you want to go further, you will not be able to run inside of your Mac, which will mean having a cloud. And you have all these problems of LLMs that the state of the art is not allowing us right now to be there. So if that answers your questions. Yep.
Thanks for the demo first. Does this agent have a memory, like to store the user context and retrieve it later?
Right now, no, but that's something that I'm working on because it's very important. I mean, it has some kind of memory, and if that works, let's say, for example, if you want to define here, as you can also define an action, you could define, for example, AI.addContext, if that makes sense. And it will be, for example, committed on your own repo with its own responsibilities. If you, for example, here add to the context a key, it will set the key and write to the repo. But you could possibly also here pass the emp.myVariable, for example. And here you will have hard-coded that the LLM always have some context. On your repo will be hard-coded that context, but you will be not leaking this to the repo itself. But it's not like, I think that are better abstractions for this than this right now. I think that, for example, right now we have this driver file which holds all the executions that are being happening to not oversaturate the context that the LLM sees and all this stuff. I think that here, for example, could be something like .memory or things like that.
I didn't see any migration folders, so that's why.
Yeah. So this is what we have right now. Where it was? Here? No, here. This is what we have right now, but I think that building a memory system is primary. Anyone, any more? Or we are shy? If that's all, thank you so much for being here. And